Well, our story does not end here. It, in fact, is only getting more interesting. You notice that if, since we know that L is an integer, 2L plus 1 must be an odd number, right? So if you put, if you expose the hydrogen atom in a magnetic field, you'll find that each level now splits into an integer number of levels, and that integer must be an odd integer of 2L plus 1. And yet, what people found was that if they had a better spectrometer, they examined the hydrogen spectrum in more detail, they found what's called a doublet structure. That is, each line is actually split into two lines. Each spectral line representing an energy level is actually split into two slightly different energy levels. It's called a doublet. This doublet really puzzles people because, first of all, it's an even number. It's not an odd number, unlike 2L plus 1. And secondly, we understand that we can put this atom in a magnetic field. It's going to split its energy levels, right? Here, we don't have a magnetic field. We just leave the hydrogen as is, and you'll find each single line is actually split into two lines called a doublet. So where does that come from? Where does the doublet come from? Is there some sort of internal magnetic field that does the trick and give it a doublet instead of a triplet, and so on? So that's something that puzzled people. And the way we understand that is by introducing what's called the spin magnetic quantum number. Historically, Goldschmidt and Uhlenbeck, two young physicists in the year 1925, proposed this idea of electronic spin. They didn't quite know what that spin entailed, but they call it spin to mimic the classical sense of a ball spinning about its axis of rotation. And they say, okay, imagine the electron is actually a tiny, tiny sphere, and it rotates about its own axis, and that spin creates an angular momentum, right? Just like the Earth, the Earth goes around the sun, it has orbital angular momentum, but also spins about its own axis. That's how we get 24 hours a day, and that has its own spin angular momentum. And we know the orbital angular momentum created a magnetic dipole moment. How about the spin angular momentum? Shouldn't also create a magnetic dipole moment, right? And that magnetic dipole moment will then interact with a magnetic field to create this doublet. But what field is that? We know we didn't put this atom in an external field, right? So that field must be produced locally inside the atom. By who? Well, actually, that's easy to understand. By the proton. Because if you sit on the electron, then from your perspective, you see the proton going around you, right? The proton is charged, and as it goes around you, it has a current. That current produces a magnetic field, doesn't it? At the location of the electron, right? And if the electron happens to have its own dipole moment, this is a spin dipole moment. Okay, remember the electron is the center of the coordinate. It doesn't move, right? You're using the electron as a center of the coordinate system. You see the proton moving. The electron is not moving. It doesn't have any orbital motion. So its magnetic dipole moment is not due to the orbital motion, rather it's due to what's called a spin. So in order to introduce this, understand the doublet idea, you have to introduce the electronic spin. That's according to Goldschmidt and Uhlenbeck. And the spin is an angular momentum, just like in classical case, spinning creates its own angular momentum. So it satisfies the angular momentum concept of quantization idea of quantum mechanics. In fact, in quantum mechanics, energy is not always quantized, momentum is not always quantized, but the angular momentum is always quantized in quantum mechanics, no matter what. The spin angular momentum is no exception. It has to be quantized. And how many possible values of the z component of that spin angular momentum do we have? Well, it looks like there are only two, because that's how we have a doublet, right? So you add the spin angular momentum, which interacts with the orbital motion of the proton. So we have this, we call it spin orbital interaction. You have a negative mu dot b term. This is mu s due to the spin dot b. This b is due to the orbital motion of the proton. We call it bl. That is the new term that will give us the split, the doublet, right? U, we call it SL or LS, so the spin orbital coupling. We call it spin orbital coupling or spin orbital interaction. And produces two levels according to experiment, and therefore there are only two possible directions for the z component of the spin. Positive, and it's positive along z and negative along z. But we know in general, if we have a quantum number L for the angular momentum, we have 2L plus 1. Here we call it the quantum number S. So clearly, we must have 2S plus 1 z components. But from the experiment, we know it's equal to 2. So what did I tell about S? S equals 1/2. Okay, this is not an integer, it's a half integer. It turns out there are many particles with half integer spins. The quantum number for the spin does not have to be a full integer. It can also have half integers. It cannot have something like 1/3 or 3/4, nothing like that. But it has to be either integer or half integer. We'll see that later. Again, that was introduced by these two young physicists, Goldschmidt and Uhlenbeck, in 1925. But when they proposed this idea, they didn't really know whether they were on the right track or not. So they asked more senior physicists for critique. And among the senior physicists who critiqued their idea was a famous one by the name of Sommerfeld. Sommerfeld made major contributions to both classical and quantum physics, and Sommerfeld did not like the idea of electronic spin. He had a rebuttal. He said, "You guys must be wrong." So what was wrong with the Sommerfeld was the idea of spin for the electron? Well, Sommerfeld said, look, if you took the electron literally at just a miniaturized Earth, okay, with a radius r, here's the radius r, and here's the equator, right? Here's the equator. So it spins like this. Here's the spin angular momentum. Spins like this, right? I know what r is. Sommerfeld says r, the classical radius of the Earth, so-called classical radius of the Earth. Don't mind where it comes from, but I can tell you, it is 2.8 Fermi. Okay, so according to classical understanding of the electron, it's a ball with a 2.8 Fermi radius. Today we know this is wrong, but in Sommerfeld's time, that was agreed upon. And he says, look, if you want to produce enough angular momentum, how much angular momentum we're talking about? The angular momentum we're talking about, S, the magnitude, equals what? S times S plus 1 times h bar, right? And S equals 1/2, so this is actually 1/2 times 3/2, that's the square root of 3 over 2 over times h bar. It's about 1.7 over 2, square root of 3, it's 1.7 divided by 2 times h bar. In order to produce this kind of angular momentum, how fast does this electron have to spin? You can calculate the spin rate, right? You set this equal to I times omega. I is the rotational inertia of a sphere, which is 2 over 5 mr squared, m being the mass of the electron, r being 2.8 Fermi. You can do that. Right? You can find what I is. You can calculate omega. Now if you go in and calculate that omega, which Sommerfeld did, he found that omega is so large, the spin electron is so fast, in order to produce this angular momentum, that a point on the equator of this electron must have a linear speed v greater than c, the speed of light. Now that was 1925. That's when Einstein's theory of relativity has been published for 20 years already. You cannot have v greater than c. Nobody would buy that anymore. So therefore, Sommerfeld said, your idea is wrong. No such thing as electron spin. But it turns out that the idea of the spin was not dead. There are experiments after experiments to convince people of its existence. We now fast forward to 1927. This is when Stern and Gerlach, two physicists, did this Stern-Gerlach experiment, which really convinced people of the existence of electron spin. So the idea was this: whatever it's spin or not, if you have a spin, which is an angular momentum, which produces a magnetic dipole moment, what can a magnetic dipole moment do if you put it in a magnetic field? Well, we learned that in classical physics, physics 1c, in fact. If the field is uniform, you put a magnetic dipole moment, which is a little colored group, right? The only thing it can do is it can turn, because there will be a torque on it, so it's going to turn. it's not going to accelerate from place to place because the total force of a uniform field on a magnetic dipole moment is zero, even though the torque is not equal to zero. However, if you put it in a non-uniform magnetic field, there will be a magnetic force acting on it. We can see that from the math here. U equals negative mu dot B, right? That's the interacting potential. And we put the z-axis along the direction of the magnetic field, so it's mu z times B. And then the force along the z direction is equal to the gradient of the potential with the negative sign, right? F equals to negative gradient U, isn't it? That's from physics 1A, right? Okay, now let's consider only the z direction. Let's say that, because the magnetic field only has a z component, so let's look at the z direction of the force. When you do that, isn't that partial B, partial z, right? Partial B. So if the B field is non-uniform in the z direction, then there will be a force acting on this dipole along the d direction, which is proportional to partial B over partial z. This cannot be zero, cannot be uniform. Okay, now, what is that force equal to? It equals to mu z times this gradient along the z direction. This gradient, whatever it is, it's not zero. As long as it's zero, as long as it's not zero, it's okay. But mu z may have different values depending on what kind of state this atom is in. The atom they used in the experiment was silver, and they chose the S state of the silver, which means L equal to zero. There is no orbital motion contribution to the magnetic dipole moment, so don't blame it on orbital motion. Okay, and then if there are 3 different values of mu z, then there will be 3 different forces acting on this beam. So within each beam of silver atom, let's say there are 3 different types of atoms with 3 different mu z values, then they will receive 3 different forces. So they're going to, after going through this, they're going to split 3 ways, right? They're going to hit the photographic plate in 3 different places. How many different places did they found? Well, classically, it should be a smeared out result, because classically, the mu z is the z component of mu, and the angle theta between mu z and the mu itself, this angle theta is a continuous variable, classically. Continuous variable, which means mu z itself is a continuous variable, which means the force is also a continuous variable, so therefore, it's going to be everywhere, okay? The beam coming in, going through a non-uniform B field, in the z direction, this is the z direction. Some forces are positive this way, some forces are negative that way, and the force varies continuously, so this beam will be pushed up and down with variable forces, variable but continuous forces, and that's what you're going to get. Okay, so on this plate, you're going to get a range of landing points. Quantum mechanically, we know it's not going to be continuous anymore because mu z is quantized. Mu z is, corresponds to Lz, which is quantized, right? Remember? And then how many different landing spots are you going to get? That depends on how many different mu z's you have, because for every mu z, we're going to have a different force, and therefore it's going to push this beam in a different direction, landing in a different spot. And what they found was that they had a pattern like this captured on photographic plate. That tells them that there are 2 different values of mu z. One giving it a positive force, pushing it up, the other giving it a negative, pushing it down. So as the beam goes this way, part of the beam gets up, pushed up, part of the beam gets pushed down, so that's why you get this. Nothing in between. Okay, now this is weird. Why is this weird? Because as we learned before, the way you split beams, you split energy levels in the magnetic field, however, different ways, that depends on different numbers of mu z, which depends on different number of m values, and there's only an odd number of m values because the total number is 2l plus 1. But now clearly it splits 2 ways, only up and down. So it's only split 2 ways. So if you want to use some sort of angular momentum to express this result, you find this corresponding quantum number is 1/2. Okay. Again, 2s plus 1 equals 2. It splits 2 ways, and then you must have 1/2. So you go back to the idea of a half integer spin, half integer angular momentum, I should say. Now, what's wrong with Sommerfield's critique? Well, nothing wrong. Sommerfield was self-consistent, except he neglected a subtle point, and that is the original Goldschmidt and Ullambek idea of the electronic spin should not be taken literally. The electrons are not miniaturized Earth doing rotation about its own equator, doing about its own axis. So you have this problem on the equator, whatever. The electrons, in modern view, are actually point particles. They do not have any radius, believe it or not. It's just a single, simple particle with no internal structure. So what about the spin? The spin is a borrowed term, okay? Do not take it literally. It's a borrowed term. We borrow this term from classical physics handily because in classical physics, both orbital motion and spin motion of the Earth produces its own angular momentum. We need an angular momentum in this case, in addition to the orbital motion of the electron. And that orbital motion, that angular momentum, therefore, is called spin. It does not literally mean the electron is a tiny ball spinning about its own axis rotation. It does not do that. No such a thing. Spin is a totally quantum effect. The only thing that is analogous to classical physics about the spin is that just like the classical real spin, this quantum so-called spin, under quotation mark, is in effect responsible for its own angular momentum. This angular momentum is possessed by the electron by itself without having to move from place to place. It doesn't have to do any orbital motion to have that. Therefore, we call it the so-called intrinsic angular momentum. The electron somehow just has that angular momentum all by itself. Okay? We borrow a term from classical physics. We call it spin, angular momentum, even though please do not take it literally. So the Zollfield critique, you don't have to worry about it. It's not that it's wrong. It's just that it shouldn't have happened in the first place if you do not take the idea of classical spin literally. So again, because of the Stern-Gerlach experiment, we know that clearly the silver atom with no orbital angular momentum for the electron splits two ways. It must be another type of angular momentum, which we now know as the spin angular momentum, splitting the beam two ways. So there are two possible values of its z component, therefore s equals to 1/2. The spin angular momentum quantum number is 1/2. Okay, so 2s plus 1 equals 2, which is supported by the experiment. It also supports the idea, the experimental finding of doublets in the hydrogen spectrum. So here is an illustration of the spin angular momentum. There are two possible ways for the spin angular momentum to project on any z-axis, because 2s plus 1 equals 2. So we have two possible ways: a positive half of h bar, negative half of h bar. Okay, again, spin is a borrowed term from classical physics. It cannot be taken literally. And it is a unique quantum phenomenon. There is no classical correspondence. There is no classical counterparts. Okay, the true idea behind the spin is that it represents the intrinsic angular momentum of a particle. The particle somehow just has an angular momentum without any orbital motion. Intrinsic angular momentum. No such a thing in classical physics. But being an angular momentum, it must satisfy all the notions of angular momentum in quantum physics. For example, what is the magnitude squared of the spin angular momentum? Well, it is equal to this, right? Add an h bar here. Now, please be careful here. This s and that s, they're not the same thing. So why don't I just do that? Okay, this s is only the quantum number associated with the spin angular momentum. This is spin angular momentum squared. It's just like, I'm sorry, not squared, because I already took the square root. It's just like L, okay? The magnitude of the orbital angular momentum L was equal to square root of L times L plus 1 times h bar. Here the same thing. The magnitude of the spin angular momentum equals square root of s times s plus 1, then times h bar. But s equals 1/2 here, so it is square root of 3 over 2 times h bar. Right here, see? The magnitude here, square root of 3 over 2 h bar. And when you project onto the z-axis, you got two possible results: a positive half h bar or negative half h bar, because ms, the z component of the spin angular momentum, is ms h bar, and that equals 1/2, positive 1/2 h bar over 2. Okay? And the angle between the spin angular momentum and its z component, theta, these two angles theta are the same, and you can actually find what value it is using this and that. Okay, I have introduced a symbol, actually two symbols. One is like this, the other is like that. This represents a spin up state. So if you see this symbol, that means this electron spin is upward, so which means the z component of the spin is positive. Here is a spin down particle, which means the spin angular moment of the particle is downwards, so we call it spin down. Just like that, there was a relationship between the orbital angular momentum and the corresponding magnetic dipole moment. I have here a relationship between the spin angular momentum and the corresponding spin magnetic dipole moment. In the past, when we derived mu L equal to negative mu B L over h bar, mu B was the Bohr magneton. Here, there is a similar formula here, negative mu B, except there is another quantity, GS, which is called gyromagnetic ratio. Now, don't ask me where that comes from. Okay, it's beyond our lecture, but I can tell you that GS is roughly equal to 2. It's 2. Excellent approximation equals 2. Gyromagnetic ratio. So this is how you go from the spin angular momentum to the spin magnetic dipole moment. And from that, we can find what kind of energy correction would arise if you expose the spin magnetic dipole moment to a magnetic field. So now the interesting thing here is that even without an external magnetic field, I just look at hydrogen's electron, the electron in the hydrogen atom itself. Okay, it has its own spin angular momentum, S. Therefore, there is a dipole moment associated with that due to the spin of the electron, and this dipole moment will then experience a magnetic interaction with what? With the magnetic field produced by what? By the proton at the location of the electron. Okay, that's going to lift the degeneracy for different values of ms, positive and negative 1, positive negative 1.5. So it's going to push level up and push level down, and therefore you're going to double it. That doublet has, the separation is very small because we're talking about mu b, which is of the order of 10 to the negative 4 or negative 5, and therefore we're looking at a very small correction. It can be only seen with a very good spectrometer, and therefore we're dealing with what's called the fine structure of the hydrogen atom.